All right, welcome to mini lesson 7. This is the last mini lesson of the first week of online PY413 content. We're going to keep talking about partition functions for internal degrees of freedom, but this time we're going to focus on the vibrational levels. I think this is not in the textbook. It's possible there's a problem or an exercise about it that I've forgotten about, but it's definitely not in the main text of the textbook. So just to remind you what we're doing, we've got something like a polyatomic molecule that can have translations of its center of mass, rotations, and internal vibrations. And when it's coupled to a thermal reservoir, it makes sense to think about its canonical partition function, which is just a product of the partition function for each of those three types of motion. So just to be clear, the translational one is the one that we did before when we just used the particle in a box levels. We did the rotational partition function last time as a specific example for a diatomic molecule. And today we'll talk about the vibrational partition function. And I think the vibrational one we can actually say quite a bit more about and be less approximate and wishy-washy. So just to remind you of the picture, we've got sort of a molecular energy diagram where we have the electronic energy is this deep well, and then the internal degrees of freedom are quantized levels within that well. So the dark red ones are the vibrational ones, and they form this ladder of equally spaced harmonic oscillator levels, where the energies are given by this expression. E of n is h bar omega naught, n plus a half, where n is an integer from 0 up to infinity. So let's now apply the machinery, the toolbox of canonical partition functions to the vibrational levels. So we can sort of just turn the crank. In this case, there's no issue of degeneracy. Each level E of n counts only once within the partition sum. So we don't have to worry about a degeneracy factor like we did for the rotational part. So we can just now plug in this energy expression into the expression for the partition function, where now we're summing over all the possible values of n from 0 up to infinity, the Boltzmann factor with these oscillator levels inside it. And so we'll do a bit of arithmetic. Let's go ahead, and this is a sum inside an exponential, so it can be turned into a product of exponentials. And one of the exponentials doesn't have a factor of n, so this e to the minus beta h bar omega naught over 2 factors out of the sum, and we're left with a sum from n equals 0 to infinity of e to the minus beta h bar omega naught times n, the summing index, or the quantum number. And so we look at this, we can actually recall that it's essentially a known sum, right? So if you take the sum from n equals 0 to infinity of some r raised to the n power, you get 1 over 1 minus r on the oopsie, I keep doing that. On the condition that the r is less than 1. And so since e to the minus beta h bar omega naught always has to be less than 1, this expression is just an example of this geometric series. So let's just go ahead and evaluate it. Again, we're factoring that out. We've got e to the minus beta h bar omega naught raised to the nth power, and we use the geometric series to evaluate the sum so that you get this thing we factored out in the numerator, and then the denominator is just 1 minus the r factor, so e to the minus beta h bar omega naught. And that's the partition function for the vibrational levels. Full stop. No approximation made. All we had to do was remember that special formula for the geometric series. So this is a really, really good result. Let's go ahead and see what to do with it. So you can definitely think about making high and low temperature approximations. You could just use the formula as it stands. It's not particularly ugly. But it is useful always to think about whether the behavior in the appropriate limits is right. So in these slides, I'd like to pay attention to the high temperature limit. And so let's consider the behavior of the vibrational partition function as beta goes to 0. So that's the high temperature limit because beta is 1 over kBT. So if you just substitute in beta equals 0, here you get 1 over 0, and that blows up. And it's true that as beta goes to 0, this partition function should kind of blow up. But this actually tells us essentially nothing. Basically, we just throw up our hands and say, oh, I guess it blows up. We're done. So it's not wrong, but it doesn't answer any question. What we need to do in thinking about the high temperature behavior of this function is to generate a function that describes how the partition function blows up as beta goes to 0, right? And that's a useful thing to say as opposed to, oh, it blows up, let's just go home. So this is one of these things within PY413 that I really think you should take with you to other classes. So for example, this idea that when you think about a limit like this, you're not just subbing in, you're really thinking about how to evaluate variations in functional behavior in the context of this limit, not just a substitution of this beta equals 0, right? And so when you want to do this, your tool is almost always going to be a Taylor expansion. So when you're faced with a limit that tells you something that is correct but useless, your tool will almost always be to do a Taylor expansion, to say something that is both correct and useful. So in the above formula, if you let beta go to 0, it means that the argument of each exponential is also going to 0. It's a small parameter. And so you can expand in Taylor series the exponential functions about 0. And so it looks like e to the minus x is approximately 1 minus x plus a half x squared minus blah, blah, blah. You can keep going. So if you look at what each term of this does, and if you just consider the first term, that's what you would get by just making the simple substitution beta equals 0. So this is the one that is certainly correct, but basically useless because it just tells you a number that doesn't help you understand the behavior of a function. So you start to get functional behavior when you take higher order terms of the Taylor expansion. So you'll now actually have a function of x that tells you how the thing behaves and changes. So what we're going to do is keep just the first order term in the expansion. You definitely want to think that through. There are going to be times when first order would not be good enough, but certainly it's a good place to start. So let's do it. Let's go ahead and expand these exponentials to first order. So e to the minus x gives you 1 minus x, where x is beta h bar omega naught over 2. And then in the denominator, you do basically the same thing, except you don't have the 1/2 inside the exponential. So 1 minus 1 minus beta h bar omega naught. And so that reduces to the 1's cancel in the denominator. That's nice. You get 1 minus beta h bar omega naught over 2 divided by beta h bar omega naught. Distribute that through, and you get 1 over beta h bar omega naught minus a half. Now as beta goes to 0, this term is getting really big, certainly compared to a half, and so we'll neglect the half in the high temperature limit. That's fine. And we get that the vibrational partition function is approximately 1 over beta h bar omega naught. And so does it make sense? I want you to play the same game that Schroeder did, only now you don't have, that Schroeder did for the rotational case, remember? But I want you to now do it untethered from the textbook, where you're going to have to apply this fact that we know that the average energy is minus 1 over z dz d beta, and see if the result that you get by doing that in the high temperature limit agrees with the equipartition theorem as we would have used it in chapter 1. So in other words, you're going to have to count the number of quadratic degrees of freedom, and they'll each contribute a half kBT. So this is the kind of logic that I'm really going to expect you to be able to employ and discuss as you do exams and homeworks. All right, and so then another issue is, could you do the low temperature case? It should be relatively straightforward to think about the low temperature case. It's not going to be a straight up one-to-one substitution of beta goes to infinity compared to beta goes to 0. You're going to do different arithmetic steps. But again, think through the idea that you just want to understand the behavior of the function. So if you just substitute in beta goes to infinity, you basically get to 0th order, you get 0. But that doesn't help us. Sorry. What you want to know is, functionally, how does it go to 0 for large values of beta in the low temperature limit? And so that's an exercise you could do by yourself to make sure that you're following along with the kinds of tools that we're hoping you'll learn in this segment. So yeah, this is a little bit of a shorter example. At this point, I want to say that we're going to be done with Chapter 6 of Schroeder, and we're going to move on starting next week to Chapter 7, where we talk about real quantum statistics. It's kind of interesting that even though we've been using quantum energy levels in Chapter 6, we're not really doing quantum statistics. And so I'll say more about that in the next mini lesson. See you later.